Hello, this video covers the lecture part of Lab 9, which is about counters and sequence recognizers. In this lab, we're going to design a 3-bit decrementing counter, and then we're going to move on to the design of a sequence detector. We'll start with the first experiment of this lab. The experiment requires us to design a 3-bit decrementing counter using D flip-flops and to test the circuit design using logisim. Just to refresh our memory on the steps required to design a sequence generator, you can read them on your own or pause the video for your reference. We'll start now with the first experiment of this lab. The experiment requires us to design a 3-bit decrementing counter using D flip-flops and to test the design using logisim. We'll start with the first step, which is drawing the state diagram. For a 3-bit decrementing counter, the first state should output the maximum number for a 3-bit counter. The maximum number we could reach with a 3-bit long number is actually 7, since 1, 1, 1 is 7, so this is going to be the output of the first state. Since this is a decrementing counter, then the next state should output 6 in binary, which is 1, 1, 0. Then we're going to output 5 in binary, which is 1, 0, 1. Next, the output should be 4, 3, 2, 1, finally 0. And just like with any counter, if we reach the last state, we're going to reset back to the initial state. Now the next step is to count the number of states. For n states, the number of flip-flops required should be the nearest integer greater than or equal to log base 2 of the number of states. Here we have a total of 8 states, so that means we need at least 3 flip-flops to implement the design of a 3-bit decrementing counter. Now the third step is to convert the state diagram into a state table showing Q and QNX for each of the flip-flops we're using. Assume that the name of the flip-flops is going to be flip-flop 2, flip-flop 1, and flip-flop 0. Then we can assume that the outputs of the flip-flops are Q2, Q1, and Q0 respectively. Here we have the state table half filled with the initial state or the current value for each of the flip-flop output. Next, from the state diagram, we're going to determine the values of QNext for each flip-flop. So on the left columns, we see the current value of Q, and then in the next clock edge or the next clock cycle, each of Q is going to update to the next value according to what we're going to specify now based on the state diagram. So initially, if the state is 0, so 0, 0, 0 means actually 0, right? So we're currently here, then that means the next state is supposed to be 1, 1, 1. So we're going to fill in the table accordingly. And then if the next state is, or the current state is 1, 0, 0, 1, which is here, then that means the next state is supposed to be 0, 0, 0. If the current state is 0, 1, 0, which is here, then the next state should be 0, 0, 1. If the current state is 3, since this is a decrementing counter, then the next state is supposed to be 2, so we're going to write 2 in binary. Now if the current state is 4, which is the case here, then the next state is supposed to be 3, which is 0, 1, 1. If the current state is 5, then the next state is 4. If the current state is 6, then the next state is 5. If the current state is 7, or output 7, then the next state should be 6. Now our state table so far shows the value of Q and Q next for each of the flip-flops we're using. The next step is to add columns for the input combinations that will result in this transition between Q and Q next for each flip-flop. So we're going to need a total of 3 columns. So D2, one is for D2, then for D1, and finally for D0. We're going to refer back to the characteristic table for a D flip-flop. According to the D flip-flop, the value of D will determine the value of Q next. So if D is 0, then Q next is going to be 0. If D is 1, then Q next should be 1. So that means we can simply create 3 columns, D2, D1, and D0, so that they are equal to Q2 next, Q1 next, and Q0 next, respectively. Notice here that Q2 next is equal to D2, Q1 next is equal to D1, exactly, and finally Q0 next is equal to D0, because according to a D flip-flop, to determine the value of Q next, we can simply choose the value of D, or the input of the flip-flop, and then at the next clock cycle, Q at the output will update to match that of D. Now the fifth step is to find K-maps for the inputs of every flip-flop we're using. We have 3 flip-flops, so we're going to start with a K-map for D2. Remember, if we assume the order from 0 to 7, like such, when we implement the K-map, remember to skip a number here. If it's a 2 by 4 K-map, then you're going to record the values, so it will be 0, 1, 2, then 3. Then in the next row, you'll have 4, 5, 6, then 7. So these two numbers are swapped actually. So we're going to copy the values of D2 in the D2 K-map as such. Then the next step is to group the ones that we have in the K-map. We'll have this one by itself. Next we have these two ones together, and finally these two ones together. This will result in the equation or the formula for D2, so that it will be equal to Q2 bar, Q1 bar, Q0 bar. And then for this group, we have Q2 and Q0. Now for the last group, we have Q2 and Q1. Moving on, we're going to implement K-map for D1. So it will be 1, 0, and then we're going to swap these two, remember. The way you record the values of the K-map, so that you'll record first the first 2 values, then the third one, then the third one is going to be here, then the fourth one is going to be here, and so on. The first K-map illustrates that clearly, but remember not to miss it. Now, moving on, or going back actually to the K-map of D1, we can group the ones that we have. We can group these two together and these two together. This will result in a Boolean expression for D1, so that D1 is going to be equal to Q1 bar and Q0 bar, or Q1 and Q0. Finally, we'll do a K-map for D0 as such. This will result in an expression for D0, so that D0 is equal to Q0 bar. Remember, we can group all these four elements together combined. Hence, the expression simplifies to Q0 bar. Now, the final step is to convert or translate the Boolean expressions obtained in the previous slide into a circuit logic diagram, so we can implement it using any software. Here I have color-coded each of the signals needed. So we have Q2 bar in dark orange and Q2 in bright orange and so on. Notice that the clock, the same clock, is actually connected to all three flip-flops that are being used here. Also, we're going to have three outputs, and the outputs are Q2 as the highest significant bit. Next, we have Q1 and finally Q0 in that specific order. Depending on the speed of the clock, we're going to see the output update, so it will count from 7 decrementally to 0 and then goes back to 7 and so on. So if the circuit is correct, the connection is correct, you will see the state diagram that we've designed earlier being displayed as an output bit here. Now we're going to move on to the second half of today's lab, which is sequence detectors. Basically, a sequence detector has one input consisting of one bit that's being inputted serially. We can name it X, for example. And it will have, or the sequence detector will have one output bit, which is Y, for example, such that Y is equal to 0 when the sequence is not yet detected at the input, and Y, the output, is going to be equal to 1 when the sequence is detected. And notice that there is only one bit at the input, but it changes serially, so you can feed in your input serially to the sequence detector and then observe the output. Once the sequence is fed completely, the output should change to 1. Here we're looking at an example that will illustrate the idea of a sequence detector further. Here we have a serial input named X and the output is named Y for a sequence detector that detects 3 consecutive ones, meaning if you see 3 ones at the input, you're going to output 1. So this is the sequence of interest, and it consists of a total of 3 bits, or the length of the sequence is actually 3 bits. Thus, initially, the output is 0, because so far we only have detected a 0, and we're interested in detecting 3 ones, one after the other. And then moving on, the sequence so far we have is 0, 1. 0, 1 is not the sequence we're interested in, so the output remains 0. Next, the sequence we have so far is 0, 1, 1, which is not what we're looking for, so the output remains 0. And then we're gonna move on by looking at simply the most recent 3 bits. Since the length of the sequence we're looking for consists of 3 bits, or its length is actually only 3 bits, so we're only gonna keep in memory the last 3 bits, or the most recent 3 bits. So far we have 1, 1, 0. This is not the sequence we want, so we're gonna output a 0. Next we have 1, 0, 1. This is not the sequence we want, so we're gonna output a 0. Next we're gonna look at 0, 1, 1, which is not the sequence we want. But finally here, the most recent 3 bits are 1, 1, 1, which is the actual sequence we're looking for. thus the output is going to update to 1. And the next cycle, the input changed to 0 again, right? So that means the most recent 3 bits are actually 110, which is not the sequence we want. That's why the output will change again to 0. So observe that for a sequence detector, the output only changed to 1 once you see the entire 3-bit sequence at the input. Here's a list of the steps needed to design a sequence detector. Feel free to pause the video to read them on your own, but we're gonna explain them as we see an example of a sequence detector one step at a time, and then implement that step. But notice or remember that the first step, or the most important step, is to draw the correct state diagram for the sequence detector. Now, before we move on to how to design a state diagram for a sequence detector, let's go over the convention state symbol for a Moore machine. For each state, as a symbol, we're gonna use a circle and then divide the circle into 2 halves, such that the top half, we're gonna put the state name, and then at the bottom, we're gonna display the output for that specific state. And for each state, we need to consider all the possible inputs and then decide on which state we're going to go next. For example, here, if the input has this specific value, we're going to loop back to the same state. Otherwise, we're going to move on to the next state, and so on. Here's an example of a Moore machine state diagram in which we have 2 states. And then if the input is 0, we loop back to state 0. If the input is 1, for example, we're going to move to state 1. And if we are currently in state 1 and the input is 0, we're going to stay in the same state and output 1 continuously until we receive an input of 1. Then we're going to move to state 0 and so on. So this is just a basic example to help you better understand the state diagram of a Moore machine. Here we have an exercise that requires us to draw the state diagram for a sequence detector that detects 3 consecutive ones. So we're going to start by doing practice exercises on drawing the state diagram. Notice that the length of the sequence is simply 3 bits. So we're going to start with an initial state that's blank and has nothing, right? So in here we're going to say scene nothing, because so far we've just started, so we don't have nothing in the memory. And in here we're going to put the output. The output so far is 0 because we don't have the sequence we're interested in yet. Now we need to consider both cases. The first case is where the input is 0. The second case is where the input is 1. If the input is 0, that doesn't count since 0 is not really part of the sequence. Remember, the sequence consists of 3 ones. So that means if x, the input, is 0, we're going to loop back to the initial state. So let me here write that our input is actually x, and the output of the sequence detector is y, and y is going to turn to 1 once we've seen the sequence. So the sequence is going to be 1, 1, 1 according to the question itself. Now, if we receive our first input, that means it's good, it's part of the sequence. So this is the case where x is equal to 1. We're going to move on to a new state, and then in the state, we're going to say scene the first one, our first one. Here we've seen nothing, right? Here we've seen 1. And then the output y is still 0 because we don't have the entire sequence yet. Now if we receive a 0, it means what we'll have in the memory is going to be 1 and then 0. But 1 0 is not part of the sequence. So let's see what we can work with by simply looking at the most recent bit. We're going to cross the oldest bit and then check if we have 0 as part of the sequence. We don't. So we're going to say we can cross this 0. That means we're going to end up with nothing, right? So we'll loop back, or we're going to go back to the initial state if we receive a 0. If we are in this state, let me name it state 1, and we could name this state 0. Now if we are in state 1 and we receive a 1, means what we're going to have in memory is so far 1 and 1, which is part of the sequence, so that's good. So what we're going to do is we're going to move on to a new state. I will label it state 2, and inside the state I'm going to say scene 1 1, and then add the output. So far I don't have the entire sequence, so I'm going to still output 0. And then here I will label the state, or the arrow here, I will label it x is equal to 1. So this is the case if I receive a 1 at the input. If I am in state 2, where I have 1 1 so far, and I receive a 1 at the input, I will have my entire sequence. So I'm going to move on to a new state, and I will name it state 3, and inside I will say scene 1 1 1, and 1 1 1 is actually my sequence that I'm looking for, right? So here I'm going to output a 1. So y, the output is equal to 1. Now the state diagram is almost complete, except I will need to take care of the other conditions. Or in here I know for sure that if the input is 0, I will go to here. If I'm in state 1 and the input is 0, I'll go to state 0. And if the input is 1, I'll go to state 2. But in state 2, I need to take care of the case where if the input I receive is equal to x, or x is equal to 0 actually. What I will do is I will copy what's inside the quotation mark, which is 1 1, and then add to it the input, which is 0. So the input is 0, and I will check, do I have 1 1 0 anywhere inside the scene? No. So what I will do is I will cross the oldest bit, and I will check what I have as the most recent bits. Do we have 1 0 at all? No. So I will cross the 1, and I will check if there's any state that says scene 0. There is nothing, so I can cross the 0, and then that means I will go to the initial state that says scene nothing. Similarly, when I repeat these steps on state 3, I will find out that I will have to reset to the initial state if the input is 0 as well. Now what I have is a complete state diagram, except I need to take care of what if I receive a 1 and I'm at state 3. In state 3, what I have in memory so far is 1 1 1. So if I receive a 1, I will have the recent 3 bits are going to be 111, and it is the actual sequence that I want. So that means if I am in the last state and I receive a 1, I will stay in the last state and I will output a 1. Now this completes the state diagram for a sequence detector that detects 3 consecutive 1s. Now we're going to do another example of a state diagram for a sequence detector that detects the sequence 110. First, we're going to check the length of the sequence. The sequence is 110, that means its length is 3 bits. So that means if we're implementing the design using a Moore machine, we're going to need a total of 4 states. And then inside of the state, I'm going to split each state so that I'll have a location or space allocated for the output y. So y is equal to, y is equal to, y is equal to. And then the first state, I will name it state 0. Second state is state 1. Then I have state 2, state 3. Inside each state, I will say scene, and then write 1 bit at a time of the sequence. The initial state, we're starting with nothing, so we're going to say scene nothing. The first state, state 1, will have the first bit of the sequence, which is simply 1. And then in state 2, you can say scene the first 2 bits of the sequence, which are 1 and 1. In state 3, we're going to put the entire sequence, so the bits 1, 1, and finally 0. Now the next step is to write the best case scenario. That means we're going to transition from state 0 to state 1 if we receive the first bit, which is this one. So if x, the input, is equal to 1, we're going to move from state 0 to state 1. If the next input bit is equal to also 1, then we're going to move on from state 1 to state 2. So notice that the inputs x is equal to 1 and then x is equal to 1 are recorded here in the memory of state 2. When we're in state 2 and we receive the last bit of the sequence, which is 0, we're going to transition from state 2 to state 3. What I'm going to write next is the output bits in each state. We only have one output, but I need to mention it or specify it inside each state since this is a Moore machine design. In the last state, state 3, I've received the entire sequence, so that means I will output a 1, y is equal to 1. In all other states, I don't have the sequence yet, so all other states are going to output a 0 besides state 3. Now the last thing I'm going to do is I will take care of any input combination that I haven't considered yet. Starting with the first state, state 0, I know if x is equal to 1, we're going to move to state 1. However, if x is equal to 0, while I'm in state 0, I'm going to loop back in state 0 and stay there until I receive my first bit in the sequence. So far, I've covered all cases for state 1. Now the next step is to go to state 1 and take care of the case where the input is equal to 0. I know if I'm in state 1 and the input is 1, I'm going to move to state 2. Now if the input is 0 while I'm in state 1, what I'm going to do first is copy this 1 as it is, and then right next to it the possible input, which is 0 that I'm considering right now. Then I'm gonna check if there is any state that says scene 1 0. If there's a state that says scene 1 0, I'm gonna go to it. Otherwise, what I'm gonna do is I will cross the oldest bit of the sequence, and then I will check if there's any state that says scene 0. There is no state that says scene 0, so I'm gonna cross this 0, and I'm gonna end up with nothing. So that means if I am in state 1 and I receive a 0, I'm gonna go to state 0. Now I took care of all the possible input combinations for state 1. I'm gonna move on to state 2 currently. And I will repeat the same process. I will write whatever is inside the quotation mark, which is 1 1. Then I'm gonna write the possible combination, or the possible input, the next possible input. I've already took care of what will happen if I receive a 0 and I'm in state 2. I know I should go to state 3. So now what I'm going to do is find out what will happen if I receive a 1. I will check if there is any state that says scene 1 1 1. There is no state that says that, so I will cross the oldest bit. Is there a state that says scene 1 1? Yes, and the state is actually the same state, state 2. So that means if I am in state 2 and I receive a 1 at the input, I'm gonna go back to state 2 again. Now we'll examine the last state. I'll check what will happen for both cases. The first case is when I receive a 0. So let's write whatever is inside the quotation mark. It's simply 1 1 0, and then write the next possible input, which is 0. And then check only the last 3 bits, because the length of the sequence is actually 3 bits. So I will cross this old bit. I'll be left with 1 0 0. I will check first if there is any state that says 1 1 0. There's nothing. Now what about 0 0? Is there any state that says scene 0 0? The answer is no, so I will cross the 0. Next, I will check if there is any state that says scene 0. There is no state that says that, so I will cross the 0. I'll be left with nothing. So that means if I am in state 3 and I receive a 0, I'm going to go to state 0. Now I need to take care of the last possible combination or possible input. If I am in state 3, which has scene 1 1 0, and I receive a 1 at the output, I will cross the oldest bit, because my length, the length of my sequence is actually 3 bits. So I will only examine the most recent 3 bits. 1 0 1 doesn't exist. What about 0 1? Still doesn't exist. Now what about just simply 1? Is there any state that says scene 1? Yes, and that state is state 1. So that means if I am in state 3 and I receive a 1, I'm gonna move to state 1. Now this completes the state diagram for a sequence detector that detects the sequence 1 1 0. Now we're going to move on to experiment 2 of today's lab. In experiment 2, we're required to design a sequence recognizer that can recognize the sequence 1 0 1, and then to test the design using Logisim. We're going to start with the first step, which is designing the state diagram. Since the length of the sequence is 3 bits, that tells us we're going to need 4 states if we're implementing this using a Moore machine. So we're going to start with state 0. In state 0, we've seen nothing because we're just starting, and the output at the bottom is 0. If we receive our first bit in the sequence, we're going to move on to a new state, state 1, and in state 1, we're going to say scene 1, and the output is still 0 because we don't have the sequence yet. Now, in the best case scenario, we're in state 1 currently, and we receive the second bit in the sequence, so the input is 0. That means we're going to move to a new state named state 2, and in this state we're going to say scene 1, 0, which is still part of the sequence. Next, if we are in state 2 and we receive a 1, that's good. So we're going to move on to a new state. We can name it state 3, and then in that state we can say scene 101, which is the complete sequence we're looking for. So for that we can output a 1. Notice that the output is displayed in the bottom in green. So only in the last state we're going to output a 1, because only in the last state we have the complete sequence. Now next, what we're going to do is we're going to take care of any possible input that we haven't covered yet. So we're going to go back to state 0 and then check what will happen if the input we receive is 0. 0 is not the first bit in the sequence, so if we receive a 0, what will happen is that we're gonna loop back in state 0 again. Now if we are in state 1 and we get a 0, we know we should go to state 2. But what will happen if we are in state 1 and we receive a 1? What we will have so far is the scene 1, or the 1 inside the state, and the 1 from the input. So we're going to have a total of 2 1s. I'm going to write them here. We'll have 1 1. We're going to repeat what we've done earlier. We'll check if there is any state that says scene 1. No, nothing, right? So we're going to erase the oldest bit, and we'll check if there is any state that says scene 1. Yes, that is state 1. So that means we're going to go back to state 1 if we receive a 1. Now we're going to check what will happen while we're in state 2 and we receive a 0. The first step is to write what's inside the state, which is scene 1 0. Then add to it the next possible input, which is 0, because we already took care of this one. So now we're gonna see what happens if we receive a 0. So far we have 1 0 0. Is there any state that says scene 1 0 0? No. What about scene 0 0? Doesn't exist, right? Finally, we're left with scene 0. Doesn't exist. So we're gonna erase this 0, and then we're gonna be left out with nothing. So that means if we are in state 2 and we receive a 0, we're gonna go back to state 0, the initial state. Finally, with state 3, we need to take care of both possible combinations. So let's start with what will happen if the input we receive is 1. So we're gonna write the sequence inside the state, and then add to it this 1 at the end. We'll have 1 0 1 and then 1. Is there any state that says scene 1 0 1 1? No. What about 0 1 1? No. What about just 1 1? We don't have it. Finally, what about scene 1? Can tell that it is state 1. So if we are in state 3 and we receive a 1, that means we're going to go to state 1. Now we'll examine what will happen if we are in state 3 and we receive a 0. So if we are in state 3, that means we have 1, 0, 1 so far, and we receive a 0. So I'm simply writing the sequence bits and then adding to it the last bit in the sequence, the last bit that I receive as the input. And then I will check if there's any state that has seen 1, 0, 1, 0. No. What about 0, 1, 0? No. Now what about just simply 1, 0? Yes, that is state 2. So that means if I am in state 3 and I receive a 0, I'm gonna move to state 2. Now this completes the state diagram for my sequence recognizer that recognizes the sequence 1, 0, 1. Now the next step is to complete the state table for that state diagram. Notice that we have a total of 4 states. So we'll use D flip-flops. Since we have 4 states, remember the formula says log base 2 of the number of states. Using that formula, we can tell that we only need 2 flip-flops to implement the design. So I will name these flip-flops flip-flop 1 and flip-flop 0. For flip-flop number 1, the output of it is Q1. The second flip-flop, the output of it is going to be Q0. Since this machine or this design has an input, unlike counters, with counters they can count on their own without any additional input. But with a sequence detector, we need the sequence bits as an input for us to be able to tell or to detect the input bits or the sequence so we can output something. Thus, when I prepare the state table, not only do I put the current state, but I also need to specify the input column. So now here's only a prepared or a template for the state table that requires the use of 2 D flip-flops and 1 input named X. Notice that the Q0 and Q1 are used for the state number, and the input X we're gonna based on the input itself and the current state, we're gonna determine the next state, just like what the state diagram is explaining. Now let's complete the table here. Notice that if we are in state 0, state 0 means the value of Q0 and Q1 are 0, 0. This translates to 0 in decimal. So if we are in state 0 and the input is 0, that means the next state is supposed to be state 0 as well, right? So I'm gonna write it as 0. Now, if we are in state 0 and the input we receive is a 1, that means we're gonna go to state 1 here. So I'm gonna write state 1. Moving on in the table, currently we are in state 1 and the input we receive is 0, so X is equal to 0. We are in state 1 and the input we receive is 0. That means we're going to go to state 2. So I will write S2 here. We're still in state 1, but the input we receive is 1. So we're still in state 1, and the input we receive is 1. If the input is 1, we're going to go to state 1 again. So that means we're going to say here S1. Next, we're going to examine state 2 and what will happen to it if we receive a 0 or if we receive a 1. Again, if we are in state 2, notice that 2 is 1, 0 in binary, so we're using Q1 and Q0, which are the outputs of the flip-flop, to indicate the state number. And X is our input. So if we are in state 2 and we receive a 0, we're going to go to state 0. So we'll write here as 0. Next, if we are in state 2 and the input we receive is 1, so state 2, and the input is 1, we're going to go to state 3. So we're going to say here S3. Now, moving on to the final state in the state diagram, state 3, so 1, 1. If the input we receive is 0, while we're in state 3, the input is 0, we're going to move to state 2. So we're going to type or write S2 here. Finally, if we are in state 3 and we receive a 1 at the output, so state 3 and we receive a 1 at the output, we receive a 1 at the input, we're going to move to state 1. So we'll write S1. Now here I've written the state name. The next step is to translate the state name into values for Q1 next and Q0 next. So S0 means 0, 0, right? Simply. S1 in binary is 0, 1. S2 is 1, 0. State 1 is 0, 1. State 2 is 0, 0. The code for state 3 is 1, 1. If you forget, you can always refer to the first 3 columns here. Back to state 2, here we have 1, 0. Now state 1 is 0, 1 in binary. Now the next step is to determine the flip-flop inputs that will result in having Q1 changing to Q1 next and Q0 changing to Q0 next. Remember the characteristic formula or equation for a D flip-flop simply states that D is equal to Q next. So we can simply copy the column of Q1 next and then write it here, and then copy the values of Q0 next and then write them as the values for D0. So I'll simply copy them as they are. We're going to have here 0, 0, 1, 0, 0, 1, 1, finally 0, and then 0, 1, 0, 1, 0, 1, 0, 1. Now the last step here is to determine the truth table for the output. If we're implementing the design using a Moore machine, that means simply the output depends on only the current state. That's why for the output, we've generated a new separate column, new separate table showing only the current states without the input. Notice that the output is written inside the state circle or symbol because it is independent of the input. So we're going to complete the table based on our knowledge of that. So the output will be 0 everywhere except at state 3. Remember, these will be used as the state number, so this is state 3. So only in state 3, the output is equal to 1. Now we have completed the state table as well as the for the flip-flops as well as for the output itself. Now the third step is to generate key maps and Boolean equations for each flip-flop that we're using and for the output. We're going to start with the flip-flops that we have. We'll start first with flip-flop 1. So that means we need to create a K-map for D1. We'll simply copy the column of D1 in a key map consisting of Q1, Q0, and X as variables. Then we can simply group this one by itself and then these two ones together. This will result in having the expression for D1 as D1 is equal to Q1, Q0 bar, and X, or Q0 and X bar. Next, we're going to generate K-map for D0 to create an expression for D0. Simply, we're going to copy the column of D0 here. Remember to skip or to swap the order of these two and the last two as well when completing the K-map. So for D0, we can group all these four ones together. This will result in D0 being equal to X. Now we're going to generate a K-map for the output by itself. Notice now that the table simplified to only a total of 4 rows because this is a Moore machine and the output depends solely on the current state. So this will result in a K-map of size 2 by 2 consisting of Q1 and Q0 as variables, and inside of it we're going to copy the values of Y, 0, 0, 0, 1. So Y, the output is simply going to be equal to Q1 and Q0. Now that we have all the Boolean expressions needed for this design, we can simply translate these expressions into a logic diagram so we can implement it using Logisim or any other software. Observe that we will need a total of 2 flip-flops. We labeled them F1 and F0, but remember to connect the clocks of the flip-flop together, just one clock. Make sure the frequency of the clock is not too fast so we can really be comfortable inputting the sequence bits serially at your own pace, so you can actually even observe the output being updated to 1. So we'll manually change the input X by inputting the sequence. So this is a sequence detector that detects the sequence 101. So what you'll do is actually notice when the clock is 0, you're gonna input the first bit in the sequence and then wait until the clock rises from low to high, so it will read in your input X, and then only do your changes when the clock is off or 0, so that when the clock transitions from low to high, it will actually read in your input. In this slide, you'll see some practice exercises. We've already explained how to design the state diagram for these sequence detectors, but feel free to actually create the state tables and the key maps to obtain the expressions and then sketch the circuit diagram for these detectors. Thank you, and if you're watching this during a live session, feel free to ask questions in the chat if you have any. Otherwise, you can email me at alat@auk.edu.kw.